Greetings and welcome to the short presentation on encryption and cryptographic techniques. In this session, we'll delve into the fascinating world of cryptography, exploring its vital role in securing digital communications and information in our increasingly connected world. We'll cover key concepts, including encryption types, cryptographic algorithms, and practical applications. Whether you're looking to safeguard data, ensure privacy, or authenticate communications, understanding these techniques is crucial. Join us as we break down complex topics into easy-to-understand explanations and demonstrate how encryption is integral to personal and organizational security. This module consists of the following 5 sections. Section 1. Introduction to Cryptography. This section provides an overview of cryptography, the mathematical foundation of information security, which converts data into secure codes and back again. Section 2. Principles of Cryptography. This section explores how cryptography provides a secure communication method using complex algorithms and keys. Its principles include confidentiality, integrity, authentication, and non-repudiation, ensuring information remains confidential, secure, and trustworthy in the digital realm, from sensitive communications to global transactions. Section 3. Cryptographic Protocols. Cryptographic protocols are rules for encrypting and decrypting data in secure communication, ensuring privacy, data integrity, and authentication. They are essential for secure web browsing, email exchanges, and file transfers, ensuring trustworthiness and reliability in the digital world. Section 4. Cryptanalysis and Security. Cryptanalysis analyzes and breaks cryptographic systems to uncover hidden messages, expose vulnerabilities, or decrypt messages without a secret key. It plays a crucial role in security by testing and challenging cryptographic algorithms and ensuring digital communications confidentiality, integrity, and authenticity. Section 5. Practical Applications of Cryptography in Network Security. Cryptography is crucial in network security, ensuring confidentiality, integrity, and authenticity of digital communications and data storage. It protects sensitive information from unauthorized access and cyber threats. Practical applications include encrypting data, using VPNs, and implementing digital signatures. Cryptography is essential for maintaining robust security frameworks in networked environments. This section provides an in-depth understanding of cryptographic techniques, including symmetric and asymmetric encryption, hashing, and digital signatures, which are crucial for securing digital information and communications and ensuring confidentiality and integrity. Cryptography is the practice and study of techniques for secure communication in the presence of third parties called adversaries. Its main objective is to ensure information privacy, integrity, and authenticity by converting it into an unreadable format for unauthorized users using algorithms and cryptographic keys. A set of fundamental terms underpins cryptography. Plaintext is the data before any encryption, while ciphertext is the scrambled, unreadable output after encryption. Encryption converts plaintext to ciphertext using a cipher, a mathematical algorithm, and a key, a secret value specifying the transformation. Decryption reverses this, turning ciphertext back into plaintext. In asymmetric encryption, 2 different keys are used, a public key for encrypting and a private key for decrypting. Symmetric encryption uses the same key for both processes. Hash functions create a unique digital fingerprint of data, and digital signatures verify the sender's identity and data integrity, similar to a seal. Cryptography is the cornerstone of network security, serving as the first line of defense in protecting information as it traverses the digital landscape. By encrypting data, cryptography ensures that sensitive information such as financial details, personal data, and confidential communications remain private and secure from unauthorized access. It plays a pivotal role in authenticating user identities, safeguarding integrity by detecting tampering, and enabling secure e-commerce transactions. Cryptography is vital for maintaining trust in the digital world, where the threat of cyber attacks is ever present. Without it, the fabric of digital security would unravel, leaving data exposed and vulnerable to exploitation. The principles of cryptography form the theoretical foundation for the secure transmission and storage of information. These principles protect data from unauthorized access, alteration, and misuse. Cryptography principles are essential for securing communication and information in digital transactions. They ensure confidentiality, integrity, authentication, non-repudiation, key management, and access control. Confidentiality ensures that information is accessible only to authorized users, while integrity guarantees data accuracy. Authentication uses digital signatures to verify user and device identities. Non-repudiation prevents denial of previous commitments. Key management ensures secure key generation, storage, distribution, and destruction. Access control enforces data access and tokens. These principles form the core of secure cryptographic systems and are applied in various contexts, including secure communications over the Internet, data protection on mobile devices, and the safeguarding of critical infrastructure. Cryptography's effectiveness in achieving these principles depends on the strength of the algorithms used, the security of the key management practices, and the robustness of the overall system architecture. Cryptographic protocols are crucial in computing for secure communications and data exchange. They utilize techniques like encryption, hashing, and digital signatures. They underpin online transactions and private communications, safeguarding sensitive data across various applications, including web browsing and digital finance. Cryptographic protocols operate behind the scenes like SSL and TLS for secure web browsing, SSH for secure shell access, and numerous other protocols that protect day-to-day digital operations. Symmetric encryption is a cryptographic technique in which the same key is used to encrypt and decrypt data. This method relies on shared secrets and fundamentally differs from asymmetric encryption, which uses a pair of keys, public and private. When using symmetric encryption to facilitate secure communication between Bob and Alice, it's essential to understand how they exchange data securely with a shared key. Here's a simple overview of the process Bob and Alice might follow to use symmetric encryption for their communications. Step 1. Key agreement or exchange. Bob and Alice need a shared secret key for secure communication using symmetric encryption, exchanged securely using a secure channel or protocol like Diffie-Hellman. Step 2. Encrypting the message. Bob uses a symmetric encryption algorithm, AES, to encrypt a message for Alice, transforming it into ciphertext, making it unreadable without the shared key. Step 3. Sending the encrypted message. Bob sends an encrypted message to Alice, ensuring that anyone intercepting it without the key would only see meaningless data. Step 4. Decrypting the message. Alice decrypts the encrypted message using the same symmetric key and reverses the encryption algorithm to restore the ciphertext to the original plaintext message. Bob and Alice's use of symmetric encryption enables them to maintain privacy and integrity in their communications, provided that they manage their encryption keys securely and use robust encryption algorithms. Symmetric encryption uses a single key for both encryption and decryption. This key must be shared between the sender and the recipient in a secure manner, as anyone with access to the key can decrypt the data. On the other hand, asymmetric encryption uses a pair of keys, a public key and a private key. The public key is freely distributed and used to encrypt data, while the private key is kept secret by the owner and used for decryption. Since only the private key can decrypt the messages encrypted with the corresponding public key, this method solves the key distribution problem. Asymmetric encryption, also known as public key cryptography, uses various algorithms with unique properties and use cases. RSA is an early public key cryptosystem used for secure data transmission, while ECC uses elliptic curves for efficiency. DSA is designed for digital signatures and is often used alongside SHA for message integrity. Diffie-Hellman is a method for securely exchanging cryptographic keys over a public channel, while LGAML can be used for digital signatures and encryption. HKCS standards define cryptographic communication, using asymmetric encryption for digital certificates and secure emails. Asymmetric encryption, a more complex setup involving public and private keys, allows secure communication between Bob and Alice, requiring two separate keys for each participant. Here's a straightforward explanation of how Bob and Alice might use asymmetric encryption to communicate securely. Step 1. Key generation. Bob and Alice each generate a pair of keys, a public key, which can be shared with anyone, and a private key, which must be kept secret. Step 2. Exchange of public keys. Bob and Alice maintain their private keys secret while exchanging public keys, allowing them to share them securely over insecure channels. Step 3. Encrypting the message. Bob uses Alice's public key to encrypt a confidential message, ensuring only Alice's private key can decrypt it. Step 4. Sending the encrypted message. Bob sends an encrypted message to Alice via a communication channel, which Alice can decrypt using her private key, as it is encrypted with Alice's public key. Step 5. Decrypting the message. Alice decrypts a message using her private key, matching Bob's public key, and converting it back into plaintext after receiving the encrypted message. Through asymmetric encryption, Bob and Alice can achieve secure, authenticated, and confidential communication, even across insecure networks, without the need to previously share secrets other than their public keys. Hash functions are mathematical algorithms that generate a unique, random alphanumeric string from an input. They are crucial in cryptography for data integrity verification without revealing the actual data. For example, passwords are stored as hash values, and they are used in digital signatures and blockchain technology. These one-way functions prevent tampering and pre-image attacks, making them essential for security. Cryptography uses key algorithms for hash functions such as MD5, SHA-1, SHA-2, SHA-3, RIPE-MD, and Whirlpool. MD5 produces 128-bit hashes, but is now considered obsolete due to vulnerabilities. The1 produces 160-bit hashes, but is insecure against well-funded attackers. SHA-2 offers 256 and 512-bit hashes, while SHA-3 offers 256-bit and 512-bit. RIPE-MD 160 is a 160-bit variant, while Whirlpool is a 512-bit hash. These algorithms are used for data integrity verification, authentication, digital signature generation, and cryptographic applications. Step 1. Input handling. A hash function takes an input or message of any length and processes it to produce a fixed-size string of bytes. The input can be anything from a short text string to a large file. Step 2. Processing the input. The hash function breaks down input into smaller blocks, performing fast mathematical operations to produce unique outputs without revealing the input itself. Step 3. Avalanche effect. The avalanche effect is a crucial feature of a hash function, ensuring unpredictable and enhanced security by causing a change in the input. Step 4. Output generation. A hash function produces a fixed-size hash value, like 128 or 256 bits, depending on the algorithm, ensuring the output remains consistent regardless of the input size. Here are some key features of TLS, Transport Layer Security. TLS Overview. TLS is the successor to SSL, Secure Socket Layer. TLS is the standard security technology for establishing encrypted links between web servers and browsers. Purpose of TLS. TLS ensures all data between the web server and browsers remains private and integral. TLS protects against eavesdropping, tampering, and message forgery. TLS key features. TLS uses stronger encryption algorithms than SSL. TLS provides mechanisms for encryption, decryption, and authentication. How TLS works. TLS initiates with a TLS handshake to share keys and establish encryption before data transmission. TLS employs asymmetric cryptography for exchanging keys and symmetric encryption for data privacy. TLS versions. TLS versions include TLS 1.0, TLS 1.1, TLS 1.2, and the latest TLS 1.3. Each version of TLS enhances security and improves performance. TLS 1.3 enhancements reduces the number of round trips required for the handshake. Eliminates outdated cryptographic algorithms, increasing overall security. Benefits of TLS. TLS secures web transactions for e-commerce, online banking, and personal data exchanges. TLS is essential for compliance with data protection standards and regulations. IPsec Internet Protocol Security is a protocol suite for securing IP communications by authenticating and encrypting each IP packet in a data stream. IPsec is widely used to establish virtual private networks and secure remote user access to the Internet. The operation of IPsec involves several key steps to secure communications between two parties. Here are the two phases of how IPsec works. Phase 1 is the initial step in establishing a secure communication channel between two endpoints over an IP network. It involves negotiating with the Security Association, SA, which includes encryption and authentication algorithms, keys, and connection modes. Phase 1 focuses on establishing a secure channel for negotiating SAs for Phase 2. A key exchange protocol, like IKE, establishes a secure channel for negotiating SAs. The duration of the SA is also agreed upon during Phase 1, which must be re-established periodically to ensure secure communications. IPsec Phase 2 is the part of the IPsec protocol where the actual data transmission is secured between two endpoints. Here's a brief overview of how IPsec Phase 2 works. Phase 2 of IPsec involves establishing security associations, SAs, to encrypt and decrypt data traffic, generating unique keys for each session. Data packets are encapsulated according to IPsec modes, such as tunnel mode for VPNs and transport mode for end-to-end communications. ESP or AH can be used for confidentiality, integrity, and authenticity. Keys can be periodically refreshed to maintain security. Security policies define traffic flows, and IPsec applies appropriate SAs to ensure that only authorized traffic is allowed. This phase is crucial for protecting data in transit over insecure networks. SSH, Secure Shell, is a secure network protocol administrators use to access remote computers, execute commands, transfer files, and manage network infrastructure. It employs symmetric and asymmetric encryption to protect against eavesdropping, hijacking, and malicious attacks, making it a crucial tool for system administrators. Here are the 4 main steps explaining how SSH works. Step 1. Establishing a connection. When the SSH client initiates a connection to the server responds with its public SSH key and version information. This initial exchange also determines what version of the SSH protocol will be used. Step 2. Key exchange and host authentication. Once the connection is established, SSH proceeds with a key exchange to set up the encryption that will secure the communication. During this phase, the client verifies the server's identity using known host keys, preventing man-in-the-middle attacks. The user is warned that the connection could be compromised if the host key is not recognized. Step 3. User authentication. After the server has been authenticated, it's your turn to authenticate yourself to the server. SSH supports several user authentication mechanisms, including passwords and public key authentication. This step empowers you to prove your access to a private key, ensuring that only authorized users can access the server. Step 4. Session. Once you are authenticated, the encrypted SSH session begins. This is the most critical phase, where commands and data can be sent securely between the client and server. The encryption and integrity of the session are maintained using symmetric keys established during the key exchange phase, ensuring the ongoing security of your communication. These 4 steps collectively ensure that the SSH protocol not only securely encrypts the session data, but also rigorously verifies the identity of both the server and the user, safeguarding against unauthorized access and data breaches. Cryptanalysis is the study of analyzing information systems to understand hidden aspects of the systems. It is used to breach cryptographic security systems and gain access to the contents of encrypted messages, even if the cryptographic key is unknown. In the security context, cryptanalysis represents a potential threat, as it involves techniques that can circumvent security measures, thereby exposing confidential data and compromising data integrity and authenticity. Cryptanalysts, often called attackers or hackers in the context of security breaches, use various methods such as frequency analysis, pattern analysis, and mathematical attacks to crack encryption algorithms. However, cryptanalysis is a crucial tool for security professionals. It identifies weaknesses in encryption algorithms and enhances system resilience against unauthorized access. Due to the perpetual arms race between cryptographers and cryptanalysts, cryptanalysis drives the evolution of cryptography, ensuring continuous improvements in practices and robust data protection against unauthorized access. Cryptanalysis involves methods of breaching cryptographic security systems and gaining access to the contents of encrypted messages, even if the cryptographic key is unknown. Several types of cryptanalytic attacks are utilized to compromise encryption algorithms and protocols, each with its unique approach and required conditions. As cryptographic algorithms have become more sophisticated, attacks have also evolved. The development of quantum computers poses a new type of threat to many classical encryption algorithms, and cryptographers are already working on developing quantum-resistant algorithms to mitigate this future risk. Cryptography is a cornerstone of modern network security, providing the tools and protocols necessary to secure digital communication and information systems. Its practical applications span a wide array of functions and services in network security, ensuring confidentiality, integrity, and authentication. Here are some key applications. Secure Communications Protocols, TLS and SSL. Cryptographic protocols such as Transport Layer Security, TLS, and Secure Sockets Layer, SSL, are used to secure Internet communications. They encrypt data transmitted over networks, including web browsing, email, messaging, and the Voice over Internet Protocol. Secure Network Infrastructure, Virtual Private Networks, VPNs, use encryption to create a secure tunnel for data to travel across unsecured networks, like the Internet, ensuring that data remains private and inaccessible to unauthorized users. The IP Security, IPsec Protocol Suite, secures Internet Protocol communication by authenticating and encrypting each IP packet during a session. Data Integrity, hash functions. Cryptographic hash functions verify the integrity and authenticity of data transferred over a network, ensuring it has not been tampered with or altered. Confidentiality, end-to-end encryption. Applications like messaging apps use end-to-end encryption to ensure that only communicating users can read the messages, keeping them confidential, even from service providers. In summary, as we conclude our exploration of encryption and cryptographic techniques, we've uncovered cryptography's pivotal role in modern security frameworks. From basic encryption methods to advanced cryptographic algorithms and protocols, we've seen how these techniques safeguard data integrity, confidentiality, and authenticity across various digital platforms. We've also discussed the importance of robust key management and the challenges posed by cryptanalysis. This knowledge will equip students with the tools to enhance security measures and protect sensitive information in a world where digital threats constantly evolve. Thank you for watching. Remember, the strength in digital security starts with the understanding and application of these critical cryptographic techniques.